For my lab, I chose to explore Felix Baumgartner's historic record-breaking jump. Using Newton's second law, I hope to model his jump as he breaks the speed of sound. Here is some footage of his jump right before he is about to descend. He jumps from a height of 127,852 feet and reaches a max speed of 844 miles per hour. In order to accurately replicate his jump, we're going to use quite a few different physics models. The first of which is Newton's second law, which states that his final velocity is equal to the initial velocity plus the net force divided by his mass times delta t. In this case, the net force is equal to the force from gravity plus the drag force. For the drag force, I choose to use a different model in order to include more forces that might be acting on it. As a whole, it's 1/2 times density times velocity squared times a c constant times the surface area. I chose to do this because the impact of density is a lot more prevalent in his jump than it is in a lot of the different other models that we've used. And also his surface area has an impact. As the pressure changes, then the surface area has more of an impact on his drag force. And finally, we have Newton's law of gravitation, which states that negative g is equal to the mass of the Earth times his mass over r squared, and r is the different distance between Felix and the center of Earth as he falls. In order to get an accurate number for the drag force, we had to use a couple more models because he has had such a high distance that the near Earth model cannot really be used. So for this, we have the upper atmosphere model that includes temperature, pressure, and density. The temperature is found by using this equation here, with h being the height that he is traveling. The pressure is then calculated using this t value, and finally we can get the density. From this density, we can then plug it into our drag force model and be able to get a more accurate representation. Each of these values act as contact forces on Felix during his fall, and each one has a slight impact on the drag force that we can then use to model his jump more accurately. In Python, we can enter some of the initial conditions, starting off with Felix's mass, which is shown here. And then I chose to create Earth to be the origin at 0, and then Felix's position to be how high he was from the center of Earth to where he first left the satellite. And I chose a different coordinate system. I used the spherical polar coordinate system because since we're only interested in tracking him and his distance from the center of the Earth, it makes it easier and a lot easier to understand. And then his initial velocity would be 0 since he's starting from the jump. Next in the code are a couple more constants that we need. First being the c constant for the drag force. And this was estimated just based on his size and what a normal human's drag force constant is. Now we have the gravitational constant, which is the g value of negative 6.67 times 10 to the negative 11. Then we have the mass of the Earth used in the gravitational force to be 5.97 times 10 to the 24th. And then the surface area, which is used to calculate the drag force, and we found that to be 1.25 meters squared. Now in the while loop, I chose to have the code run until he reaches the speed of sound, which is 343 meters per second. First off, we need to find our r value, which is the position of Felix minus the center of the Earth squared at each calculation. And then using that r value, we can then calculate the force from gravity with the negative g times the mass of the Earth times his mass over the r value. And then we need to calculate the temperature change as he falls. All of these next couple work to calculate the drag force. So we start out by doing the temperature, which is just calculated here. And then we calculate the pressure using that temperature value. And finally the rho value, which all of these can be then combined into the drag force model that I showed you earlier. And then using that drag force model, we now can find the net force by adding the force of gravity and the drag force. Once we have the net force, we can use Newton's second law to predict his velocity as he falls. Using that, we can then calculate his position. And once we have that, we'll know where he was when he breaks the speed of sound. When we run the code, we are given these final results. We have the time to be 36 seconds, which is when he reaches the speed of sound. His final position, which would tell us that he then traveled 6,455 meters. And here is his final velocity, or the closest time step we could get to the speed of sound. And it's off by about 4 seconds when you look at the actual jump. He breaks the speed of sound at the 41-second mark. And a couple things that could contribute to this would be most likely in our drag force model. Since there were so many calculations and we had to use so many assumptions for things such as the surface area and the constant, then we're not going to get a perfectly accurate drag force, which would impact how long it takes him to reach a certain speed. However, it's fairly close, and even with a velocity that's about 20 meters per second off, we have a fairly accurate representation of his record-breaking jump.